Welcome to ECE595, Statistics 598 on Machine Learning 1. Today we are going to talk about lecture number 35 on maximum loss attack and regularized attack. Before we go into the technical details, let me give you an overview of what we are going to do today. Last lecture we talked about minimum distance attack. It is one of the three forms of adversarial attacks. We went over the linear case, and then we bridged to the deep neural networks. Today we are going to consider two other forms of attacks. One is the maximum loss attack. The other one is the regularized attack. Same as the minimum distance attack, we are going to look at the geometry and also the formulation in the linear case. And then we're going to talk about how to extend these ideas to deep neural networks. So here is the outline of today's lecture. There are two parts. In the first part, we are going to talk about the maximum loss attack. And then we're going to talk about the regularized attack in the second part of this lecture. So first, let me talk about the maximum loss attack. Now, if you look at the formulation of the maximum loss attack, you realize that it is also an optimization, very similar to the minimum distance attack that we have seen last time. However, the difference here is that instead of trying to minimize the distance, which is the distance between your optimization variable x and also your current data point x0, we are going to maximize this function, which appear to be in the constraint of our minimum distance attack. So effectively, we are switching the role between the constraint and also the objective function from the minimum distance attack to the maximum loss attack. Now, why is it called the maximum loss attack? Let's look at the constraint first. First of all, the constraint says that my optimization variable compared to my input data point x0 has to be no bigger than a parameter eta. So this eta is giving you the upper bound on the distance that x can travel in the adversarial attack setting. How about the objective function? The objective function consists of a difference between two terms. The first term is the discriminant function evaluated at the target class. And then the thing that we are going to subtract will be anything that is not the target. And so if you try to recall what we have talked about before, here is our decision boundary. And then this is your data point x0. And then here is your input class ci. And then here is your target class ct. You have a discriminant function g of t here, and then you want to evaluate the value of this x that has to be sitting in the target class. And if you apply the discriminant function to evaluate this number, it has to be higher than anyone else in the decision boundary caused by other classifiers. And so this maximum operation is the same as saying that gt of x has to be bigger than any gj of x for all the j's. That's not the same as your t. And therefore, if I can maximize this difference, it means that if I have a data point x, its likelihood to appear in the class t has to be higher than anyone else in the space. So if I can maximize that, then probably I can go into the wrong class. Now, you want to differentiate between the maximum loss attack and also the minimum distance attack. In the maximum loss attack, what you are doing is that you define an eta ball around x0. Now, of course, the eta ball has to be sufficiently large enough so that within this eta ball, you will be able to go to the wrong class. For example, in this case, this is the radius of the ball, and suppose this is eta. And within the eta, you can see that there is a range of areas where it can be misclassified. Certainly, if your eta is too small, like in this case, okay, if you're in this case, then for whatever direction that you are picking, you will not be able to go into the wrong class. And therefore, the success or failure of your maximum loss attack really depends on how you choose your eta. Now, this parameter eta is, of course, related to the minimum distance attack, where we have an epsilon over there. And so for the right choice of epsilon and for the right choice of eta, the solution between the maximum loss attack and also the minimum distance attack, they will be equivalent. Let's restrict ourselves to a simpler problem of only looking at a two-class classification with a linear classifier. So in this case, what we are going to do is that we are going to minimize this function. Now, if you go back a little bit to the previous slide, you realize that we are originally solving a maximum problem of GT minus a max of something. And here I can switch the role of these two terms, this term and also the other term. Once I flip them apart, then you can see that I'm taking the difference between GT and max, and I can turn the maximization problem into a minimization problem. In addition, if I only consider a two-class problem, then I do not really need to worry about this max anymore, because there are only two classes, either your target class or your input class. Furthermore, if I restrict myself to a linear model, then each j of x has to be written as a w transpose x plus w0 for different j's. And so if you plug this equation into the objective function here, then you can show that the problem can be simplified to this very, very simple problem, where the objective function is a linear objective function with a constraint that you have a norm applied to the difference between x and x0. So when you look at this problem, you realize that this is nothing too different from a standard quadratic minimization problem, and therefore we should expect to have a closed form solution. Now let's go into the technical details a little bit more. Let us focus on the choice of using a L2 norm for our constraint. So in this case, what we can show is that you can define a variable r as x minus x0. And once you define that, then you can show that the objective function would become this. And then the constraint would become this. Okay, now it makes a lot of sense because previously you will have x here, and then here you have x minus x0. And if I replace the variable using r, then you can show that the objective function becomes w transpose r plus some constant, which only involves the x0s and also the w's. The constraint is, of course, the two norm applied to your perturbation r. So at this point, I'm going to use the technique that I introduced in the last lecture, which is to apply the Holder inequality, or in this case, it would be a special case using the Cauchy inequality to find an upper bound, find a lower bound on the objective function. And consequently, if I can find you a solution that can really meet the lower bound, then I have found the minimizer. So what I would do is that I'm going to look at the Cauchy inequality, which says that if I am looking at the inner product of w and r, it will be lower bounded by the negative of the product of the two norm between w and the two norm of r. Now, this is true by the Cauchy inequality. How about the next step? Well, because by the constraint, I know that R2 norm is upper bounded by eta, and therefore, if you put a minus sign, it has to be bigger than minus eta, and therefore, according to the constraint, I can show that this quantity is bigger than minus eta times the 2 norm of W. And consequently, I can reach the conclusion that W transpose R has to be bigger than or equals to minus eta times the 2 norm of W for any R. So now, if I look at this inequality, I realize that for this objective function, now, of course, this beta, this B0 doesn't really matter because it has nothing to do with the R, so you can ignore that. Now, once you ignore that, then you realize that the objective function is just W transpose R, and I can find you a lower bound on this objective function, and it holds for any R that you choose. And therefore, what I need to do now is really to find a particular R that can make this inequality into an equality. If I can do that, then I will be able to find the minimizer, because the minimizer will be the one that can attain this lower bound. So what would be the candidate R that I can consider? Well, I am considering this candidate, which says that R equals to minus eta times W divided by the 2 norm of W. What I would do is that I'm going to substitute this R into here and see if I will be able to reach the lower bound. So let's do some simple calculation. If you do the W transpose R, you put this R into the equation, then you have W transpose of this R, this quantity, and then you can do the inner product of W transpose W, that will give you 2 norm square W, but you also have a 2 norm of W in the denominator, so they will cancel out. That will give you minus eta times the W 2 norm. So you can compare this equation and this term here, and you realize that they are exactly the same. And therefore, by choosing the R equals to minus eta times W divided by the 2 norm of W, this will actually help you reach this lower bound. And therefore, the solution is indeed this R equals to minus eta times W divided by the 2 norm of W. So we have solved this problem with this solution. So we ask, is it possible that we can also extend the idea to L infinity norm? And here is the problem. Suppose you want to solve this objective function with the constraint, now replacing the norm by an infinity norm, then in principle, we should be able to solve a solution using a similar technique. So what I'm going to do next is to show you a closed form solution of this L infinity norm problem, and then we're going to draw a connection from this L infinity norm solution to what we have seen in the beginning of our adversarial topic on Fgsm, the fast gradient sign method. That was a very popular adversarial attack method. So in order to understand Fgsm, we want to first understand the L infinity norm, and to do that, we really need to solve this L infinity norm minimization. Now, how do we solve the L infinity norm minimization? Well, we can sort of do the exact same trick as what we are doing before. We're replacing the x by this variable r, where again r is x minus x0, and then here just shows you what is the B0. The B0 only involves x0 and also the w's. And therefore, this slide shows you that the problem that you are going to solve will be this linear objective function with a constraint, very simple constraint, that you replace the 2 norm by the L infinity norm. So how do we solve this problem? Well, we can apply the Holder's inequality, which says that if I take the inner product of W and R, and that would be lower bounded by minus the L infinity norm of R times the L1 norm of W. Now, what is the L infinity norm of R? The L infinity norm of R, as we defined, it has to be less than or equals to eta, and therefore you will have minus eta. Exactly the same approach as what we did in the L2 case. And so what is the argument then? Well, the argument is really to find a particular R that can help you reach this lower bound. And the candidate that we're choosing is R equals to minus eta times the sine of W. So you can plug this R into the equation here. Then you can see that you are taking the inner product of W transpose R. Then it will give you minus eta times W transpose the sine of the W. Now let's do some calculation here. The W transpose of the sine of W is really the summation of the ith element of W times the sine of the ith element of W. Now the sine of Wi is either plus 1 or minus 1. It is plus 1 if Wi is positive. It's minus 1 if Wi is negative. And so if your Wi itself is a positive number, then you're going to multiply with a positive number. If Wi is a negative number, then you're going to multiply with a negative 1. And therefore, no matter what you do, you will end up having the absolute value of Wi. And therefore, you can replace this Wi sine of Wi by the absolute value of Wi. And since you're summing over all the Wi's, that will give you the L1 norm of W. And therefore, you compare this equation to here, you can see that indeed you have reached the lower bound of the objective function. And therefore, the solution is R equals to minus eta times the sine of W. So I hope with these two examples, I can convince you that beyond using the Lagrangian approach, you can also try to use this approach to find the lower bound solution by finding the lower bound and then finding a particular solution to find the minimizer. So at this point, we are also able to conclude that for maximum loss attack, the geometry is also fairly straightforward, where you have a decision boundary and then you're going to draw a x0, and depending on what kind of norm that you're using, for example, if you're using an L infinity norm, then you are really just drawing a bunch of squares, and until if your eta is big enough, then you will be able to find a region that you can go into the wrong class. So to summarize, this maximum loss attack really takes the following form, where you have x equals to x0 minus eta times the sine of the W. Okay, so here is the solution. You can see that it is very simple, that you have a current data point, and then this is the step that you are going to take in order to go to the wrong class. If you compare this result with the minimum distance attack, you can also see that in the minimum distance attack, you don't really have this eta term. And what does that eta term become in the minimum distance attack? Well, it becomes this quantity. This is exactly measuring how far that you are between your data point x0 and also your decision boundary. Okay, so this, if you want to measure exactly what is the distance, it would be W transpose x0 plus W0 divided by the one norm of W. However, if you're using just an eta in this L infinity norm case, then you're really putting a box here, and that eta is not necessarily the same as this distance. And so the conclusion is that in the minimum distance attack, you are really finding a good eta such that you will hit the decision boundary. In the maximum loss attack, you need to pick the eta. So now let us talk about the Fgsm, the fast gradient sign method. The fast gradient sign method was originally proposed by Goodfellow in 2014. The idea is exactly the same as our maximum loss attack. So let me describe this fast gradient sign method, and I want to illustrate the idea using the notation as follows. So we are going to define a loss function, which is the difference between your target and also anything else in the space. So when you have this a loss function, This loss function is really saying that your target minus everyone else, that is the loss. Or in other words, you want to say that this is your target class. Target class, of course, has to be a bad class. A bad class minus one of those has to be good class. And so, of course, this good class has to be lower than anyone else. And therefore, when you try to do the training, this is defining the loss. Certainly, you want to minimize this loss. This is your training procedure. When I give you data sets, I want you to train a good classifier, then certainly you want to minimize the loss as much as you can. However, if you try to do the attack, you're going to do the opposite. You're going to maximize the loss as much as you can. Also pay attention to the variable that you are doing when you're using during the training and also the attack. During the training procedure, what you're going to do is that you are going to find a very good W such that the loss is minimized. In the attack, is different. In attack, you're going to find a very, very bad X such that your loss will be maximized. Okay, so one is trying to make the classifier as good as possible. The other one is trying to make the classifier as bad as possible. So how do we attack a classifier like this? Now, recall what we have done in the minimum distance attack. When we are encountering a deep neural network, the standard strategy is to linearize the deep neural network. In this case, we're going to linearize our loss function as follows. So it is a function in terms of X and W, and remember that we're doing the attack, and therefore everything has to be with respect to your X or the perturbation R. Okay, so suppose I have a small perturbation R that is added to your data point X0, then you can do a first order approximation by writing J of X0 plus the gradient times the R. So if you write this equation in this way, then by maximizing this is equal to maximizing the linear approximation. So you can put this equation into your objective function, then that would be your problem. So now we can also try to replace the maximization by a minimization by introducing a negative sign. And so the max becomes min, and then this will still stay as the L infinity norm less than or equals to eta. And so if you look at this objective function here, this is your objective function. You try to do a one-to-one matching between this problem and the L infinity norm problem we just introduced. And you can see that there is a very clear solution. The solution is R equals to eta times the sign of minus the gradient of the loss function. So here is the equation that you would typically see in the Fgsm literature. So the fast gradient sign method by Goodfellow in 2014 says that if you give me a loss function, then Fgsm will create a tag by doing this. You have x0, and then you have a plus of all the eta times the sign of the loss functions. Now it becomes a plus because previously it was a minus, but then you have also another minus here, and therefore the two minus, they cancel out the effect, it becomes a plus. So the corollary is that this Fgsm is actually indeed a maximum loss attack. So it says that the Fgsm can be formulated as an optimization by solving this problem. So if you read the original paper by Goodfellow, you probably will not realize that this very simple sign perturbation approach actually comes from this maximization problem. And indeed, this maximization problem comes from this thing called the maximum loss attack approach, which you have a very, very generic principle to describe all these attacks. Notice that the maximum loss attack that we're describing in this lecture here is not only applicable to the linear models. But even for here, when you do the first order approximation, you can attend the deep neural networks. This is an example that I found from the original paper, not the original paper. There's another paper that was published in 2017, which shows you the effects of the Fgsm. And in this case, they are not doing the L infinity norm; they're doing the L2 norm. And so you can see that as the strength increases, you have more and more perturbations going on in your image. However, visually you don't really see the difference, and you can also read the original paper, then you can see that the class will be misclassified into other objects. If you do Fgsm, you can choose to do either a L2 norm or an L infinity norm. So you can put an L2 here, or you can also do an L infinity norm here. If you choose to do an L infinity norm, then the solution is given by this equation. It's the L infinity norm Fgsm. You can also do the L2 norm Fgsm. Then you will run into this equation. Okay. Now, you see that these two equations are very similar. You also have this eta here. That will be the step size. And then the search direction, one is given by sign. The other one would be the normal vector of your loss function. So the Fgsm is a one-step attack, and people then come up with different ideas of making the attack even stronger. And so there is a technique called the iterative Fgsm, IFGSM, or some people call it the projected gradient attack. So the idea is that you can do this fast gradient sign attack iteratively. If you look at this loss function, the loss function, if I apply the first order approximation, I can write it as the 0th order term and then the first order term. I can get the first 0th order term here, and then I can group any term that involves x and terms that does not involve x. And so, as far as the objective function is concerned, this term doesn't really matter, and this term also doesn't really matter, because what you're going to do is that you're going to maximize with respect to x. So if you put this objective function into here, then you can see that the problem becomes maximized, just this term, with the constraint that your perturbation has to be upper bound by eta. This is also quite practical, because you want to say that your image is bound between 0 and 1. So if you do that, then you can introduce an iterative linearization idea, which says that at the kth iteration, I'm going to solve this objective function and this constraint, and then I will have to keep doing this over and over by finding a better and better xk. And so the optimization problem will become this, and you can pretty much solve this optimization problem using the standard one-step Fgsm. Now, why is that? Well, because this is nothing but a linear objective function. You can just treat it as something times your x, and this something is evaluated whenever you have the xk ready. Then you solve this objective optimization problem. This constraint will just become a projection onto the set between 0 and 1. And therefore, you can solve this iteration over and over by finding a different k, so that you can keep updating your xk. And once you get the solution multiple times, you will end up having this solution. It's called the projected gradient descent attack, or PGD attack. And it's so far the strongest attack when I do the literature search. It's still very, very powerful. Now, there is one more method that we are going to study in the next lecture. It's called the gradient masking attack. But before that gradient masking, then projected gradient descent is one of the most powerful attacks in the literature. So you can also try to add random noise to XK to make it less predictable. So in what sense? Well, so you can also add some additional ID Gaussian noise or other types of noise or other forms of randomness to this X here to just make the defense harder. Okay, so we have seen enough about this maximum loss attack. I think I have convinced you that the maximum loss attack is just a variation of the minimum distance attack. There is a very interesting connection from the maximum loss attack to a very famous deep neural network attack method called the Fgsm. We draw that connection, and we have also seen how this idea can be generalized to a more powerful attack called the PGD attack. This projected gradient attack says that I'm going to run the Fgsm multiple times, and the more iterations I go, then the stronger perturbations I can create for your decision boundary. So when we come back, we are going to look at one more types of attack, which is the regularized attack, and then we will introduce the linear model, and then we're going to look into one particular attack form is called a CW attack.